Let's take a look at calculus with hyperbolic functions. So recall the definitions for hyperbolic functions. Sine, we know is e to the x minus e to the minus x over 2. Cosh, e to the x plus e to the minus x over 2. We're going to start just differentiating sine. Okay, and with it being a show question, let's do it in exponential form. So if I wanted to differentiate e to the x minus e to the minus x, all divided by 2, so we can think about them both separately as being divided by 2 separate functions. The derivative of e to the x is just e to the x, so that would become e to the x over 2. Derivative of e to the minus x would be minus e to the minus x over 2, which would give us e to the x plus e to the minus x, also known as cos x. Very similar one for cosh. Derivative becomes sine. Just be careful with that, because obviously you used to the trig functions. We know sine differentiates to cos. Cos differentiates to minus sine, but cosh differentiates to sine. I mean, I'm sure you guys could see that for yourself just very quickly if we did it. d by dx, e to the x over 2 plus e to the minus x over 2 would equal e to the x over 2. Differentiating this one, multiply by the negative, which would be sine. Okay, so what we're going to do in this video, we're going to look at like a couple of slightly different applications of differentiating these new hyperbolic functions, so like sine and cosh. We can approach them from an exponential position, but most of the questions we just want to basically assume that we know the derivative of sine would be equal to cosh, because they will expect you to know that, unless it's like it specifically says show this using exponential form. Moving forward for the rest of these questions, I'm just going to assume that we can use these two facts. The derivative of sine is cosh, the derivative of cosh is sine. Example 2 says differentiate sec, or the hyperbolic version of sec. The rules that we can use for these derivatives are sort of summarised. We've got the bracket to a power shortcut from the chain rule. We've got the quotient rule as well. If you think about this one, if we want to differentiate sec, that's 1 over cosh. Don't forget the third letter will tell us which one it would represent. And we've got two options now. We can do it as a quotient rule, but it's not strictly a function divided by a function, is it? It's probably easier if we think about it as a bracket to a power. So we can write it as the derivative of cosh to the power minus 1. So shortcut for bracket to a power, times by the power, times by the derivative of what's inside. So if you differentiate cosh, you get sine. And then take 1 off the power. So that would give us minus sine over cosh squared. Obviously we could leave it like that, but I'm just thinking about tidying this up, like, because there's a general result that we could maybe use, which might help later. We can think about that as minus sine over cosh times by 1 over cosh, which would be minus than times by sec. Example 3 says use derivatives of sine and cosh to show that the derivative of tan is equal to this. So specifically wants us to use the derivatives of sine and cosh. If you think about it, if we're going to differentiate tan, we can write it as sine over cosh, which definitely lends itself to using the quotient rule. So we could say u is equal to sine, the derivative would equal cosh, v would equal cosh, derivative would equal sine. So if we do v times by du, that would be cosh times by cosh minus u times by dv, which would be shine times by shine, all divided by v squared, which would be cosh squared x. There's two ways to proceed now. One way we don't know yet because I haven't actually shown you this identity. Actually no, so we will have done this identity already. But there's one identity that we should sort of default know from first year. I'll show you two ways actually. So looking at what we're trying to get to, if you think about the answer, it's nice sometimes to work backwards with these show questions. Like we know that that is 1 over cosh squared x. And looking at what we've got here, like that clearly what we've got on top must be 1. Because if it's going to end up looking like sec squared, 1 over cosh squared, we've got something over cosh squared, which must be 1. We should just write down the identity that we're using there. Cosh squared minus sine squared would be equal to 1. Like it's always useful to state the identity that you're using, especially in these show questions, to justify where the answer comes from. The other way to think about it was we could split it up. So cosh squared divided by cosh squared. Minus sine squared divided by cosh squared, which is 1 minus tan squared. And again, you could state the identity there, 1 minus tan squared is equal to sec squared, if you remembered that identity. Example 4, we're trying to differentiate x times tan of x squared. Clearly we're going to do the product rule, but we're also going to have to be careful with this because there's a function inside the function. So we're doing a chain rule with this one and a product rule overall. Okay. If you can remember the shortcut for the chain rule, it will help. You can do it as a substitution as well. I would recommend that you remember the shortcut. So what's the derivative of tan? Okay, we know so far from previous example that tan differentiates to sec squared of the angle, which in this case is x squared. But we have to multiply the front. This always happens in the shortcuts for the chain rule. The derivative of what's inside, which would be 2x. So we'd multiply the front by 2x. You might not be comfortable jumping straight to that. Like, I'll show you where this comes from using a substitution. We could say y equals tan of u and u equals x squared. So when you get a function inside another function, you can just use a simple substitution. dy by du. So tan differentiates to sec squared du by dx would equal 2x. And something you've seen a lot of in A-level maths, like if you've got dy by du and du by dx, but you want dy by dx, that would be dy by du multiplied by du by dx. So from this substitution, if we multiply these together, dy by du, which is sec squared of u, times by du by dx, which is 2x. So that would give us 2x sec squared of u. Now don't forget, obviously, if you are going to do it as a substitution like this, just remember to replace it back. So u is just x squared, isn't it? I strongly recommend that you try and remember just getting used to the chain rule and how it works. Like the functions inside, which is x squared, than, we know, differentiates this x squared. Because it's x squared, multiply the front by the derivative. And that will always work on these differentiation questions if it's a function inside the function. So du by dx would equal 1. Therefore dy by dx. U times by dv, so that would be 2 x squared plus v times by du. Okay, 2 examples left, and these are both similar to the ones that we've done previously. So maybe pause the video and have a go, see how you get on. So for this one, we're going to find the derivative of Coth, and we want to get minus Cosets Squared. Quotient rule for this one, we can think about it as u equals Coth would be the derivative of cosh over shine. So if we let u equal cosh and v equals shine, so v times by du would be shine squared minus u times by dv, which would be cosh squared, all over v squared, which is shine squared. Again, maybe work backwards a little bit, see if you can get to this answer to help you. Sorry, that's going to be minus 1 over shine squared. So clearly on top here we've got minus 1, but the reason why we have is that is minus cosh squared minus shine squared. And just as good practice, write the identity down when you're going to use it. So at this point, just reference the identity. Cosh squared minus shine squared is equal to 1, isn't it? After you're taking the factor of minus 1 out. Okay, so for the next one, we're going to differentiate cosec. So we can think about it as 1 over shine, or shine to the minus 1. Bracket to a power, times by the power, times by the derivative. Take 1 off the power. We're aiming to get to this as our answer, so minus cosec, it's got coth here. That would be minus cosh over shine squared. And we can split this up to minus cosh over shine. Times by 1 over shine. So we're aiming to get to minus cosec coth, so that'll be minus cosh over shine. 1 over shine. As required. Okay, for the last one, we've got cosec squared 3x. So we can clearly just use the chain rule and the shortcut for this. Okay, we know that if it's cosec squared, it goes to minus cosec coth. So if it's cosec squared 3x, we want to be able to use this result, but we've got to think about it as cosec squared, so it's a function that's being squared. This is going to allow us to use a chain rule, isn't it? Times by the power, times by the derivative of what's inside. Okay, so if we differentiate this one, we can use the result that we've just found. So that would be minus Be careful with this. The derivative of cosets is minus cosets coth, but because it's 3x, we'd also multiply by 3. So we times by the power, times by the derivative, take one off the power. And let's just tidy this up. That'll give us minus 6 cosets times cosets coth. Okay, thanks guys.